They can. They can. That's why I was just trying to really get a feel for. Okay, we are functional here, but last class was quite scanty as far as people showing up. So I was just curious. So 3 choices.
Was the last class in person? No.
This is our first time back in person. So, oh, I'm sorry. Previous to this class period, I'm in the same room. Previous class period. So, yeah, it was pretty lightly attended. So, as far as folks that are here, preference for being in the classroom for as the default. That's just what we're doing. Okay, or okay, no opinion. Because that's what the department and the dean really encourages, and that's what our plan is. So it's not like it's going to change. How many like having the ability to do the remote for part of the time here? That worked real well for me. I had nominal symptoms to deal with and was able to do most of the classes and everything. It certainly made it nice to not have an interruption. How many would just as soon like, wow, it'd be neat if we could just do all of it online, go back to what we used to have like last year? Not so much.
I mean, exams in particular are something that I'd like to do in person.
Yeah, I tried to find some alternatives. I will have the last of the grades done. I didn't release any of them, make them visible until I have the last probably like I think 20%. I'll get those. That's my priority when we get done here, and so you'll have your grades for the exam this evening. The reason I hid them, I think I said it before, but they come up with like, everybody got like a 30 out of 80 or whatever it was, because most of the answers have to be manually checked by me. So the grader is incredibly inflexible, and
You're flexible.
And I am flexible, but it doesn't let me put in. I mean, I can put in alternatives. I can put in alternate answers that might be correct, but I can't. Like for the you have to come up with every type of graphical difference with spaces and not spaces and everything else, because you can't just say, I would, if I were implementing this stupid thing, I'd do something like, oh, I don't know, have the option for, but it's probably only computer scientists that would even think of, like, yeah, ignore spaces on this answer for me, or
We put some regex in there.
yeah, let me put that in.
Even just a way to be able to draw shapes and stuff on an exam.
Yeah, and again, the plan was to have it on paper, and I'm trying to be, I'm actually being pretty forgiving on that, with realizing it's kind of hard to convert it, and I'm having to draw out all the alternative DFAs that you came up with. There's actually probably 3 major patterns that come out from what you produced with the state names and the transitions and stuff, but it's that's slowed down the progress. What I could do in literally a matter of seconds in looking at, here's the drawing that you drew, and I can see, oops, you got this, you're looping here, it has to go this way. That would take me all of half a minute maybe to grade it, correct it, and have it come out the other end.
But now you gotta go, is it with government stuff now?
Yeah, so that's and that, I mean, obviously, when the class was completely online, that was the same problem. So, and I didn't like it then, and I don't like it now. So, the plan will be we'll have a nice in-class exam for the next exam. Okay, so where are we now? And we are talking about
Oh,
PDAs. Yeah, PDAs, our friend the PDA. Push down automaton adds a new feature. One of them or some of them. It has memory, and that turns out, where are we going? Why are we doing all this stuff on machines? You might be asking. Well, we're working our way kind of along a continuum is the word, where we started with the simplest kind of machine, which is just a state machine, right? And you can do some limited stuff with that, right? You can take the state and when we do something like, this, where we're requiring, we can associate a meaning with this, right? I've seen a single bee, and now if I do this jump, I've seen two bees. I'm assuming that we're trying to either, in this with the except over here, it's looking for strings that somehow have two consecutive bees in them. And if we wanted to prevent more bees, we could have a dead state or get back out of there, or whatever, right? But the idea I'm just trying to connect with is I haven't seen a bee sequence at all yet. I've seen one bee along the way, and here I've seen two bees, and maybe that satisfies some condition. So we have minimal tracking of the history through this thing. And in particular, if we have some kind of a loop, maybe we have an A here, looping on A's there, then we really, we can't make very conclusive decisions. All we can say is, I've seen a B, and maybe I've seen a bunch of A's before that. But the 2B sequence is kind of locked in by the states, and that's the only mechanism we have. When we get to the push-down automaton, we're adding memory. But we're adding memory with a little asterisk next to it, that it's a stack memory. What do you know about stacks? Are stacks random access? Yeah, a stack is last in, first out. And that means you can only access it from one end. We usually draw them like something like this, right, where you can only get the top element off, and if you want to add something, you can only put it in at the top. And so whatever you added last, that's the thing you're going to get back out when you try to do a pop. So you push stuff on, when you pop them off, they come off in reverse order. Most recent one, last in, is the first one out. So it's not as flexible as like a totally random access memory, right? You can't, by definition, if you really wanted the third item down, you'd have to somehow keep track. I mean, you could conceivably have some states. We'll look at how the states and transitions are defined, but you could conceivably have a series of states that popped items off and could get the third item down, but at the loss of all the other items that when you pull them off, they're gone. So it is not a very flexible mechanism. It's a limited memory, but we're kind of looking now at the classes, your basic DFA or NFA. Guess what? It recognizes a certain class of languages, regular languages, which are pretty simple. Series of characters, you can keep track. It becomes really unwieldy if you're trying to get, I only want strings of length 20, right? How do you do that? The only mechanism is via states, and you have to have how many states, what's the minimum number of states you would need if you wanted to limit your string to 20 characters?
Yeah.
I think you can do it in 21.
Yeah. Well,
So each transition, it consumes the letter, right? So it's like if you want 20 transitions, you need 21 states to jump between to get there. Right? You can't have any looping, because as soon as you put one loop in, pumping lemma says, well, if you put one in, you can put as many as you want. And so you lost your criterion, your maximum of 20 or whatever. Same with a minimum number. You're kind of stuck with, you have to have a bunch of states that you have to just go through the states in order to count up before you get to an acceptable length or whatever. So push automaton is going to have, let's look at, on page 115, and take a little bit of time just to, we'll vary it a little. We'll do, instead of 0 to the n, 1 to the n, let's do a to the n, b to the n. And we'll look at what's the strategy to accept this language? We know a DFA can't do it, right? Now, the tricky part is could a to the n, a string a to the n, b to the n, ever be in some regular language?
no. Regular.
Is it in Is this string contained in this language? Is this string a member of this language?
It is. It's an exclusive member.
Right. It's not exclusive. Right. So the point being that, sure, you could do this. This string is in here, and it's also in here. So there's nothing exclusive about it. This won't prevent that, right? That's also in that string. So that's just the point. So how can we limit? What we need to do is accept only, you give me 3 A's, then I've got to see 3 B's.
We have a DFA that has if statements.
That's an if statement, something that's missing from DFAs. We kind of have an if statement, not explicitly so, but a PDA does let us do some things with the transitions. So let's talk about what's the strategy. How do you count? If you're, remember that old saying, if your only tool is a hammer, then all your problems start to look like nails. Well, and your only tool is a stack.
Oh.
You kind of have to adapt your problems to be stack members, I guess. I don't know. Okay, it breaks the analogy. Falls up the bottom there, but
You're a hammer, everything looks like a nail.
we know we have is a stack. Everything looks like something that can be pushed on the stack. Well, how would we count something like this? Let's just take the approach of, well, if I could mark all the A's, if I could somehow tell that I can accumulate something along the way, right, and accumulate A's, something that marks off my A's, then when I get to a B, then I could start unmarking them. And if I don't try to run off, if I run off the bottom of the stack, that meant what? That I had more B's, right? If I see all the A's, and what I'll do is I'll just start pushing the symbol, well, I just used the letter. So if I see an A, I'll just start pushing A's on the stack. And when I get to the point of seeing B's, I'll pop A's off the stack. So if I see this string, what would I do? I push the A's on, 1, 2, 3, right, in order. And then when I see a B, I go, oh, if the top of the stack is an A, take it off. Next letter is a B. If the top of the stack is an A, pop it off. Next letter is a B. If the top of the stack is an A, pop it off. And when we said, I believe we hit, did we talk last time we hit the criteria for acceptance, right? There are 3 items. What does a PDA have to do to accept? You have to have 3 conditions, which are, first one, use up the string. Yes. So you don't have any leftover characters, right? And second thing, be in an accept state. So you have to have gotten to the accept state. And the third thing is you have to have a stack emptied out, right? So that's how, if I ran into this situation, if I push A's on there, and oh, see a B, pop it off. See another B, pop off the A. I'm done. Oops. My stack isn't empty, so I can't accept. And then the other, just if I had 4 B's, I'd get this A popped off. But then I'd have an extra A. I'd have an extra B over here, and I need to put in the logic that even though the stack is empty, I shouldn't get to an accept state. Even though I've used up the input, I shouldn't accept unless the stack got emptied by using up these characters, right? So that's the strategy behind it. So let's draw one here. This is going to look a lot like the one in your book, page 115. We'll have a start state. And one thing that I think I mentioned, make sure, it does not have an empty stack indicator. You can't, there's no if statement, right? Or you can't say if stack is empty, then do something. So, I mean, you could, what we're looking at is, kind of the base, the cheat model with no fringe, no options on it of our PDA. So, we're going to, we're just going to stick a $sign on at the very beginning for our stack. And that will, when I see a $sign, I can look at the top of the stack and use that to guide me to say, okay, the stack is empty and my input is empty, so now I can go to the accept state. So that's kind of the reasoning behind it. So the first thing this guy's going to do is just on an epsilon. I'll just draw them like that. So with no input consumed, don't care what's on the top of the stack, just put a $ on there. That's what that means. The transition includes the character that you're looking for and the stack option or the stack operation that you want to do when you do that transition. So the kind of new feature on the PDA is that on the transition, you look at the character, and if you take that transition, you consume that character, so you use it up, move ahead in the input, and you also have the option of doing something to the top of the stack. So the effect of this would be, let's look, I'll draw it the same. He's got it kind of in a little square. He misnumbers his states. Q0, Q1. Let's be real computer scientists here. So obviously you can draw this any way your little heart desires as far as your arranging of the nodes. But I'll just say if I'm mapping what he did. We're seeing one of the kind of clever, let's see, look, here's what we have to work with. We have a state machine, we have a stack, and so how can I do something useful with this? Okay, so the first thing that this will do is put a $ on. Now this is non-deterministic. I hope we stressed that before. What does it mean? If there's no move, we're going to look for A's here. If there's not an A present, then we can't do anything. We would come to a screeching halt if there's no transition that we can make. Right? So just like an NFA, where remember you could run off the end here. If we're using A's and B's, if this were an NFA, and I see another A, if I'm in this state and I see an A, oops, there's nothing I can do. So it would be like what the DFA would go to a dead state if in that situation. So similarly, it just stops. If there's nothing it can do, then it doesn't do anything, and it does not accept. All right, so if I see an A, I would like to push an A on top of the stack. I could do whatever, right? But in this case, we'll just use the same character. Now let's see. Will we use the same character? Oh. Just for fun, let's see. I'm trying to make this more universal, I guess. Don't care what's on top of the stack. Let's replace it with a capital A. Just for fun. Now, if I see a B, so my alphabet just and my stack alphabet doesn't use the capital gamma. Let's say has the A and the $. So this is the language alphabet, right? So any input strings must use lowercase a's and b's. And this is the stack alphabet. And the only characters that you can then push or pop would be in that set. All right, so pressing on, if I see a B and there's an A on top of the stack, replace it with an empty string. In other words, pop. This is a push operation. This is pop operation. It's just replacing, right? I mean, internally, I mean, our interpretation or use of the stack means when it sees this, it's going to push a new item on. And when you see something that matches on top of the stack, so this says if you have this on top of the stack, then pop it off. And you can only take that transition if everything matches. So you need the B there, and you need the A on top. Otherwise, you haven't got a complete match. If you have the epsilon, you don't care what's on top of the stack, and you're just adding a new item onto the top of the stack with that. Okay. So if now we can, as long as we're seeing B's, we'll do the same thing. So this, we'll talk about what the meaning of our states is. The meaning of this state is, I don't have anything on the stack, I'm just starting out. And so I'm going to stuff a $sign on there. The meaning of this state is I'm seeing A's and I'm pushing capital A's just to mark them and keep track of what's going on. This state says whatever I saw before, there was an A on top of the stack and I saw a B, and now I'm repeatedly seeing those. Or well, I mean, I may see more than one of those. But then the final little catch that gets us to the accept state, so our accept state is over here. And remember, we have to pull that non-determinism in order to remember, it's going to try every possible way. That's the probably easiest way to think about it. It's going to try every possible way to see if it can use up the string, get to the accept state, empty the stack. To meet those three criteria. So if there's any possible route that can be traveled and get you there, then it will do that. And this would be the I don't care epsilon. If there's a $sign on top, replace it with an epsilon, popping it off. Okay, so let's see. Some of the questions that kind of, one of the things I think that bothers people is maybe cleaner. Is no, wait a minute, you can't just jump over there randomly without assuming a character. You're supposed to do an epsilon move on there.
Without the $sign at the bottom of the stack.
You gotta have the $sign on the bottom of the stack. And if you happen to be there and there's characters left over, somehow, here's the machine, but maybe, the alphabet includes the letter C. And so you gave it A, B, B, C. Well, you could go through the stack, you could match up all the A's and B's and get over here, but you'd still have some to the left over. And that's actually what would happen, even if those were B's. You could maneuver, there would be a path to get to the accept state, but there'd still be leftover characters in the input string, so it would not actually accept.
So would there be a null state or not?
There's not a null state as such. In other words, not an explicit one. All right, so if we, if we trace, let's trace a good one first. This should accept, right? So this should be a multimedia here. That one should be a good one. So what would we do? Let's just trace how would this machine, this is a PDA definition, how would it respond to that input string? So let's see the A, or first thing that happens, we click it on, and first thing it does is put the $sign at the bottom and jump to state 1, as I remembered it. Then it's going to see this A, and it's going to take this, don't care what's on top of the stack, push a capital A on, and move forward. It's going to look, my input is A, again, don't care what's on top, push an A on there. That's pretty neat. Next character is a B. There's nothing, that loop won't work. And so what else can I do? Oh, if I have a B, if there's an A on top, I can just replace that with an empty. So I see this B, and I pull that A off. And I get down to here. Everybody tracking that? And we're just going to keep doing that. This is every time you see a B and there's an A on top of the stack, pop it off. So I'd see this B, match the A, pop it off. At that point, the input's consumed. I'm sitting here, and I can go, oh, I can make an epsilon move. If the top of the stack right now is a $sign, just remove it on your way by. And then I would end up here. Stack is empty. Now, I wouldn't know the stack is empty. I mean, I guess you can't check whether the stack is empty, but that's why we put the $sign on there, so we can use this logic to get over to it. So I guess internally, the machine would recognize that stack is empty. There's no more input. It's in the accept state. We made it. So we probably should look at the failure modes as well, just to be complete. Too few B's. What would happen? We'd go $sign A. That's where we get to through consuming these two A's. Okay? And now we see a B, and we go, oh, okay, I see a B. A is on top of the stack, pop it off, and go here. Do that. We do that.
What is?
What's that? Well, we're assuming, however, it doesn't really specify like end of line character or something, but it doesn't. The empty string. Well, what we would do, we'd have the A and the $sign are still sitting there. When I get here, I go, hey, wait a minute. Epsilon is a $sign on top? No. So it would be stuck here with no more input, so it can't do that. Top of the stack is not a $sign, so it can't do that. And so it would stop there with non-accept state, stack's not empty, and it used up the input. So it's the red light comes on, non-accept. And then the other end would be, so this would be a stack, and give some context. Stack underflow, it didn't use up the stack. The other possibility is you got too many B's. Stack underflow. I guess it's not Yeah, Stack Overflow is not. Erase that statement. It'd be too much stuff on the stack compared to what you wanted. It's not a Stack Overflow. It sounded good at the moment. Sorry. So I saw 2 A's here.
It's nice to see.
And yeah, it just felt good. So I see this B, and it gets me to Q2.
And you know, bubbly.
And I would have popped that A off. I can do that, pop the A off. And I still got this guy sitting here, but I would try this transition because, hey, I don't care what I'm looking at, $, take it off. It would, attempt that and get to Q3. Yeah, I got to Q3, I emptied the stack. And the only problem is, oops, didn't use up the input. So it would have to say, okay, so that path failed. What else could I do? I got a B, and oh boy, there's no A on top of the stack. Crud. That's what that's what the machine actually says. Sometimes it'll even, depending on what brand you buy, they can either get a little spicier in their comments, but you don't want to turn on the voice. Alexa, accept my A to the N, B to the N string.
Oh, crud.
It's a time by yourself in a room with a camera. Changes you, man. Okay, any questions about the mechanism here?
What if we had like an A and then a B and then an
Good question. I mean, kind of the same, just a and a B, that'd be happy, and then, oops, another A out here. We would get there on the first one. Oh boy, I see a B, I get an A on top, see that, and the same old story, we try to get over to Q3, and then we got this A anywhere off the end that we haven't done anything with, and there's nothing we can do with it.
But what if we had 2 A's and a B and an A?
Now, I can't do all of them. But, no, that's reasonable. We got 2 A's on there. We go here, push the first A, here, push the second capital A. Here, we would see that, take that path, take that A off. Then we see an A, there's an A on top of the stack, but we don't have a transition on A from Q2. So again, we would hang and say, can't do anything more, you can't do all 3 things, right? Empty the stack, use up the input, get to the accept state. There's just not a way to do that. Okay, so how easy are these things to implement? We're actually going to take a little side trip shortly here. That's not in the text, but it makes these things way easier to deal with. Can we build the? I think we did this previously, but let's write up the CFG corresponding. Oops, not GFC. CFG for those be ends. CFG for A to the N, B to the N. Can you give me one. Let's start with S. What should it do? Let's say, I should tell you, right, n, let's do n greater than 0. So what would a CFG for that look like? The way, how does the CFG do the matching? Well, you kind of build the common trick for doing something like that is to build from the outside and work your way in. So every time I add an A, I have to also add a B. So it would look something like, we can do it in one variable by doing something like this, or, so I said n greater than 0. So one, I can derive this just by going S becomes AB. Or I can do, so here's a derivation, derive the parse tree for that looks like this. It's easy to do. A, B, B, B. Again, we most often think of CFG as generating strings. So I do a derivation. If I want to make a string that is in the language, I just start substituting stuff, and I can enumerate the steps that will get me to all, right? A derivation ends in all terminals. So remember I said you kind of got to keep track of some of those definitions. So when we say terminals, it means characters that are part of the alphabet of the language but are not replaceable. They're not variables. Non-terminals are the, for convenience, right, by convention, the capital letters and within the CFG, and they are can be substituted using the rules that you supply. So every non-terminal equals variable has at least one rule associated with it that it can be replaced by. So a derivation of this would go something like this. And I'll do that same substitution again, replace S with ASB. And the old, all right, this is from, here's step 1, and those guys stay there. And then finally, I'll apply this rule and just replace, so I have the A, B, 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 like so. And parse tree for that. When we do, we start with the root of the parse tree is always the start symbol. And we replace the children of each non-terminal are the text of one of the rules for that variable. So we would, the children of S, as we chose it here, and we try to make the tree as useful, as readable as possible. We kind of stretch the connectors so that the terminals end up on the same row. Otherwise, they'd be scattered around at different heights. Right? Same lineage, same connectivity, but we're just making it more readable. So this S would be replaced by an A, a B, and another S. So at each level down the tree, we have one rule applied. And finally, this S would go to that, oops, would go to this rule, give it just the two children. Okay, it's fairly intuitive once you see it and starts to look familiar. It isn't very tricky. So what about more complicated? Let's look as things start getting more complicated. 115 is the description of the language for the automaton on 116. We're looking at A to the I, B to the J, C to the K. I, J, and K are greater than or equal to 0, and I equals J or I equals K. So it is, yeah, let's see if I'm going to reuse, I might want. I'll keep that. So the language greater than or equal to 0. Sounds a little more complex, right? So let's just talk about how might you do that. It's non-deterministic. So what does that mean? It's non-deterministic. I can kind of take the right path, right? So I have to check for two different things. Either I is equal to K or I is equal to J. And if you look on page 116, we start with the traditional push a $sign on. This is the figure 217. And now we have two different paths that we can take. If I see an A on state, so figure 217, state Q2 does what? Well, in state Q2, every time I see an A, I push an A on the stack. So that's going to accumulate A's. And then I have two different paths without doing anything, right? It's like total epsilon move. Don't care what's on top of the stack. Don't do anything with the top character on the stack. So Q2 branches into a Q3 and or to Q5 on without consuming input. Okay, then from there, if you see B's, and there's an A on top. So this is what's the top path to Q3 matches B's. So we're thinking of that non-deterministic thing, right? So it's doing both possible checks, or we can say it's doing all possible checks, and it's going through um, potentially think of trying every possibility. So if it goes, when it tries the upper branch, it's trying to match B's to the A's. So that would be either I equals J or I equals K. So that means either the same number of A's and B's, and we don't care about K's, don't care about C's, or it has the same number of A's and B's, and we don't care. Just and say it. Either it has the same number of A's and B's, don't care about the C's, or it has the same number of A's, C's, and we don't care about the B's. So that top path takes every time I see a B, if there's an A on top of the stack, pop it off. And when I get all done, if I see the $sign, that means I used up all the A's. So that means, like, what is the condition at to leave Q3? To leave Q3, you have same number of A's and B's, and then you just pop off C's because you don't care. And that leaves you using up C's. Now, what if you find another A? Well, you're not going to get, there's no transition on A from Q4 or B. So any other mix of characters that you find will just hang you up. You couldn't use up the input. You're stuck in Q4. It's an accept state. You emptied the stack, but you can't get past the leftover characters. And then similarly, if you take the other route, this says, you see B's, who cares? Just leave the stack alone. Just get B's, right? The A's got pushed on in state Q2. So we got however many A's we found. As soon as we see something that's not an A, we jump over. If it's a B, we just loop through and move past the B's. And then the C's try to pop off the A's off the stack. And again, you, in this case, the first one, the accept state Q4 had to burn past the extraneous C's. And the lower path, Q7, doesn't have to do that because we already matched the A's with the C's. So if we get to the end there, again, empty stack, accept state. And if you didn't use up the input, then the string's not in there. So once you start seeing these, I think they become a little more comfortable as far as seeing, okay, so what we're really trying to remember with the DFAs and stuff, one of the problems was it's often easier to see the path to the accept, but more difficult to see how do I make sure I don't accept stuff accidentally or stuff that's not in the language. And that kind of comes out here that the only, the key when you're trying to build your PDA to match is you've got to make sure that you can only get to the accept state with the right characters. Right? And it kind of naturally, if you got something that doesn't match, you kind of have a minimalist number of transitions that get included in PDA, because anything alternative to that just kind of gets, you get stuck on purpose, you get stuck and can't advance, and you have characters left over, and that's how it fails, that's how it doesn't accept. So that's kind of a contrast, that's different from certainly the DFA, right? DFA, you always use up all the characters and you always get to either an accept state or a non-accept state. So that was pretty straightforward. The PDA, the NFA was a little bit different, right? That you could end up with extra characters and no way to use them up. And that was a non-accept. And now we've added in the stack, which does the same kind of thing. You gotta meet all the criteria. And so your job in designing one of these is that you have to find a path that only works with the desired pattern that you're looking for. And now an interesting one is the palindrome problem.
So would it basically be like the same PDA for this one? As in,
Yeah. The palindrome is saying it is written with the this means reversed. So you have the same pattern. You don't know how many characters there are, but whatever you can say for that, this is the mirror. Maybe say mirrored series of characters for that. So what would an example be? We might have A, B, B, and the reverse of that would be B, B, A. So that would match. This definition requires an even number of characters, right? However long this is, this one has to be exactly the same. So it doesn't allow for like a middle character to be different. Just the way that definition is. We could talk about how we could fix that. Because I know that is just on your mind, like, oh man, we can only do even palindromes. What? Huh? So to keep you from being up all night, we'll try to address that. Okay, so let's just, what do we want to do? We don't care. And again, this is going to illustrate the non-deterministicness, that's the word, of the whole scheme. Because what we're going to do is if we see in, they use zeros and ones, but hey, they don't call me Maverick for nothing. Well, they don't call me Maverick either, but in any case, let's just, we're going to make our own kind of music here. We're going to walk on the wild side.
Is this the same language as L?
Say it again?
Is this the same language as L?
L.
L.
Oh, yes. No. We're down to this. Two. Over alphabet. Exactly. A, B. So this is a series of A's and B's configured such that somewhere there's a split where the first half of the word is the mirror image of the second half of the word. Okay. So our nice little non-deterministic move here says, well, if you feel like it, oops, if you feel like it, stop making too many squiggles, don't make curly braces. We're going to have to go back to remedial teacher school again. I think we got it. So a slight variation. This is a variant of 219. Our own way. Okay, so can we trace, what would we do with this nice string? It's a good string and very fine looking string there. And it should match our pattern. So does our machine accept A, B, 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 A? Certainly. I hope it does. And we trace it. First thing we do, pop that $sign on there. That's good. Now, if I see an A, which I do, I'm going to push in capital A, just for differentiation on there. Cool, I used up, I'm going to move it over here. All right, so I moved along, I saw the A, looped, and looped on Q1. Q1 says, when I see an A or B, I'm going to just add it to the stack. That's not going to quite know what's the problem here. Or where do we have to count on the non-determinism? Well, I don't know when to switch. So I see an A, I see this B, I'm going to push a B on there. I see this B, I'm going to push another B on there. And I know it reused material sometimes. As Shakespeare would say, so is it 2 B's or not 2 B's? I know. I think I used it twice, so. I didn't use it in here, I probably used it in my other class. 2 B's or not 2 B's? Well, non-deterministically, we don't care. We're just going to pick the right one. You can imagine I could try the path that goes, oh, see a B, push another one. See a B, push another one. See an A, push another one. What do I care? Got infinite stack space. And that would get you to fail, right? Because then you ran out of input, so you can't do anything. So it would back up and try all the varying paths. But we, as the highly intelligent college folk, can figure out, you know what? Just looking at this, I'm guessing that a really good choice would be to take this little whoop. And so whenever you hear the machine go whoop, that means it's taking an epsilon with an epsilon. So doing nothing on the stack. The teacher tells us stuff, but the machine making noises, and I never know whether he's telling the truth or what he's doing. So if I take this, then I see a B. There's a B on top. Cool. Pop that baby right off of there. I see another one. Whoa. And I see an A. Whoa, 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 whoa. There's no B on top of the stack. But wait a minute. How cool is that? It's that being by yourself. No camera. Just messes with you. So we get there, and this makes kind of a, and it comes over to here, and score. It would accept, and I would leave to you to play around with variants. What if you threw another A in the middle or something? You wouldn't match, right? The only way it can match is if it picks the right one. Keep pushing this on until you get to the middle, but it doesn't know where the middle is. So we just have to keep trying. Oops, that didn't work. But all the different possibilities until it finally gets to the one that works. That's kind of cool. Takes a little responsibility off. Now, what about that? How could you possibly make it work with an additional A or B in the middle? What do you think?
You could, for the transition from Q1 to Q2, just add A or B in addition to epsilon.
Yeah. How about we put fit it in there. On this thing. I'll push there we go. There it is. It's just do the same thing, but use up an A. A's are cheap, B's are cheap. If you add this in, then that allows the odd length. And I'm trying to get you feel comfortable with this non-determinism stuff. Because your first thing is you want to go, well, what if it accidentally uses up that B on that transition? Then it's going to be a world of hurt. It fails that one and it tries again, right? It just keeps going back. If there exists a way to do it, then it'll find it. And so with that little mod, we can do. How would I, right? I guess it'd be like WAWR or WBWR. So it'll allow the odd length. So we want all three of those, right? We want this would accept this or that. So it'd be the union of all those possibilities. I think we'll call it a day with that. So one of the problems, quickly, is in conclusion, and I'll go on for another 15 minutes. In conclusion, this is kind of tedious in the, you got to kind of see the clever way to use the stack. Turns out there's another way we can approach accommodating any CFG and building a PDA that will accept that CFG in general. And it turns out to be the beauty of non-determinism hits again. And it turns out to be a very simple process to create a PDA off of a CFG directly. Now this is not in the text, but we'll go over it and it will be something that you'll need to know how to do. So we'll call it a day. Now, 2 minutes later, and we should be planning for in-person stuff. The plan is to record these as long as the technology holds up. So if you can't possibly make it, then you can watch it or dial in remotely.